In this video, we will cover some common questions that follow after we find out the Maclaurin expansion of an equation. After we find the Maclaurin's expansion of an equation, we can very easily find out the equation of the tangent of the curve at x equals to 0. This is because the Maclaurin expansion is a polynomial expansion at x equals to 0. So as an illustration, if I have this curve as the original function, I am using a horizontal line to represent the curve. If I'm just using the single term here, I'm using a linear line like this to represent the curve. And if I am doing a quadratic approximation like this, it will be a curve that probably looks something like this. Thus, we can see that the first two terms over here should give us the equation of the tangent, since it is using a straight line to approximate a curve at x equals to 0. In example 1, we are asked to find the Maclaurin expansion for y equals to tangent x up to and including the x cubed term. Once we get this Maclaurin expansion, it will be very easy for us to write down the equation of the tangent at x equals to 0, because it is simply all the terms until and including the x term. So let's find out what's the Maclaurin expansion first. We get dy over dx equals to secant square x. The 2y over the x square will be equals to 2 secant x times secant x tangent x, which becomes 2 secant square x tangent x. Next, we want to simplify this expression slightly before I perform another differentiation. So this becomes 2 times 1 plus tangent square x times tangent x, which becomes 2 tangent x plus 2 tangent cube x. Now this form is slightly easier to differentiate because I do not have to perform product rule anymore, and hence that is the reason why I have changed it into this form first. If you prefer, you can differentiate this term straight away as well. There is no issue with that at all. Now for the third derivative, the cube y over the x cube will be equals to 2 secant square x plus 6 tangent square x secant square x. Now let's find out the values of all these derivatives when x equals to 0. When x equals to 0, I know that y will be equals to 0 because tangent 0 is 0. dy over dx will be equals to secant square 0, which gives us 1. The second derivative, the 2y over dx square, will become 0 as well because tangent 0 is 0 and tangent cube 0 is again 0. Lastly, the 3y over the x cube will be equals to 2, which comes from 2 secant square 0. Okay, tangent square 0 gives us 0, so therefore this term goes away and we are thus left with a 2. And with this, we can say that tangent x can be approximately x plus 2 x cubed over 3 factorial and so on, which is x plus 1/3 x cubed. And therefore with this, I can say that the equation of tangent at x equals to 0 is going to be y equals to x, since I am taking everything of the Maclaurin series up to and including the x term. We might also be required to derive the Maclaurin series of another expression, say for gx, based on the Maclaurin series of fx that we have already found. In questions like this, we don't have to repeat the entire process of multiple differentiation in order to obtain the Maclaurin series of gx from scratch. Instead, what we have to do is to establish the relationship between fx and gx. Some common relationships are, number 1, gx is the derivative of fx. And in this case, we simply have to differentiate the Maclaurin series of fx to get the Maclaurin series of gx. So for example, if we know that gx is equals to the derivative of fx, it will be the same as the derivative of its Maclaurin series a plus bx plus cx squared, and thus this will give us b plus 2cx as the Maclaurin series of gx. Next, we can also have the relationship where gx is fx with its x being substituted with another function of x. For example, gx can be f of negative 2x. So maybe we might have gx equals to f of negative 2x, and therefore this gives us a minus 2bx plus 4cx squared. Lastly, we can also have the relationship where gx is a product of fx and another function for which the standard series is known. For example, we might have gx equals to fx multiplied by e to the power of x, and therefore we can have a plus bx plus cx squared multiplied by 1 plus x squared over 2, and so on. And we just have to expand this multiplication over here to arrive at the Maclaurin series of gx. In example 2, we are asked to obtain the Maclaurin expansion for y equals to tangent x up to and including the x cubed term. And thereafter, we have to find the expansion for y equals to secant square x up to and including the x squared term. So from example 1, we have already derived the Maclaurin expansion for y equals to tangent x. We know that tangent x is approximately x plus 1/3 x cubed. Now, we just have to establish the relationship between tangent x and secant square x. So we know that secant square x is in fact just the derivative of tangent x, which is d over dx of tangent x. And therefore this becomes d over dx of x plus 1/3 x cubed, which becomes 1 plus x squared. So the Maclaurin expansion for secant square x is just 1 plus x squared. Next, another common question type is, since we know that the Maclaurin series is just an approximation of the actual curve, there will be errors as we move away from x equals to 0. And the error can be specified to be maybe 5% or 10% of the original value, and we are required to find out what is the corresponding x values such that the Maclaurin expansion is within the acceptable error margin. And to find it, we simply have to solve this inequality where fx minus f of the Maclaurin expansion series of x, the modulus must be less than the specified error. And we can solve this inequality using the GC. In example 3, we are now asked to compare the Maclaurin expansion of y equals to tangent x versus y equals to tangent x. So from example 2, we know that tangent x is approximately x plus 1/3 x cubed. So now we want to find out the difference between these two and the range of values such that the difference is less than 0.1. So with this, we can key into our calculator the graph of y equals to tangent x minus the Maclaurin expansion for tangent x, like over here, and y equals to plus minus 0.1. With this, the graph will look like this, and what we want to do now is to find out the range of values of x from here to here, where the range of error is going to be between minus 0.1 to 0.1. So we just have to solve for these intersection points, and based on GC, we can say that x must be between negative 0.876 to 0.876. And this is how we solve for this kind of questions which want us to find out the range of values of x within a certain error bound.